Okay, we'll start our discussion with the practice problem, first practice problem, which has two parts. This is a simple problem which asks that we are given an lengthened sequence X. So start with problem A. We are given a lengthened sequence where n is an even integer, and we are interested in computing the DFT of that. So all we have to do is remember the DFT formula, which is x of k is summation n from 0 to n minus 1 xn e to the minus j 2 pi k over n times little n. So in part A, what we have is that xn is 1 for even n and 0 for odd n. So I can write that as x0 times e to the minus j 2 pi k over n0 plus I have the 0th term, so I don't count that, x2 e to the minus j 2 pi k over n times 2, and this keeps on going, plus x of, now x of n is integer, is even, so x of n minus 1 is odd, that will be 0, so we'll go up to x of n minus 2 e to the minus j 2 pi k over n times n minus 2. So we have just the even indices, and I can collect them into a compact form. I can say I have n equal to 0 up to n by 2 minus 1. So I have n by 2 terms. X, now each term is actually the even term only, so I have to do x of 2n e to the minus j 2 pi k over n times 2n. So you can verify that this equality is the same as the equality above. Now at this stage, we want to make use of, we want to be careful about a few things, and at the end of the day we want to make use of the geometric series formula, which is that if I'm given n equal to 0 to, let's say, m minus 1 r to the n, that is equal to 1 minus r to the m. So 1 minus r, the total number of terms in the summation divided by 1 minus r. This is a formula that we have seen many times. This is true as long as r to the m, 1 minus r to the m is, and 1 minus r, they are not simultaneously 0. Right? Otherwise you are doing 0 divided by 0, which doesn't make any sense. So we have to be a little bit careful about those kinds of terms. Other than that, we can just use this summation formula. Right? So what are those cases? One is, for example, if my k was equal to 0, if k equal to 0, then this summation is trivial. If k equal to 0, what is the term in each? What is each of the terms? So if k equal to 0, each of these terms is 1, and you have a total of n by 2 terms. So if k equal to 0, you have x of 0 is simply equal to n by 2. Okay. The other case that you have to be careful about is if k equals n by 2. Okay. If k equals to n by 2, then again I'm going to focus on e to the minus j 2 pi by n. I have n by 2 times 2n. Okay. So this gets cancelled with n, 2 gets cancelled with 2. I get e to the minus j 2 pi n. Okay. So for k equal to n by 2, each of the terms inside the summation is e to the minus j 2 pi n. So that is simply equal to 1. Just use the Euler's identity. You have an even multiple of pi, and you get 1. So if you do that, then for k equal to n by 2, you also have n by 2 terms of 1. So you get x of n by 2 equal to n by 2. Okay. Now there are no other cases where you have this simple expression. So for that, we will have to use this geometric series formula. So for all k not equal to 0 n by 2, we can simply use the geometric series formula. We have x of k equal to summation n from 0 to n by 2 minus 1 e to the minus j 4 pi k over n times little n. Okay, so my r is e to the minus j 4 pi k over capital N. So this means that my summation, if I use the geometric series formula, I get 1 minus e to the minus j 4 pi k over capital N. How many terms do I have in the summation? N by 2. So n by 2 divided by 1 minus e to the minus j 4 pi k over n. Okay. Now you can verify that this denominator, because we have excluded k equal to 0 and n by 2, the denominator is never equal to 0. But if you focus on the numerator, what you get is 1 minus e to the, so I'm just going to cancel these things. Okay, so I get 1 minus e to the minus j 2 pi k over 1 minus e to the minus j 4 pi k over n. Now this is again, you have e to the minus j an even multiple of pi. So whenever you have e to the j an even multiple of pi, that is simply 1 by Euler's identity. So I get 1 minus 1 over 1 minus e to the minus j 4 pi k over n. That is equal to 0. So this means that my DFT of the sequence is equal to n by 2 for k equal to 0 and k equal to n by 2, and it is 0 for k equal to 1, 2, n by 2 minus 1, n by 2 plus 1, up to n minus 1. So for all k other than 0 and n by 2, my DFT is 0. Okay. Okay, now I want to go back to the part B, which is very similar. The only thing I would clarify in this is xn equal to an for n from 0 to n minus 1, and I will say that a is not equal to 1. Okay, I'm going to make the assumption that a is not equal to 1 so that I can make it simpler. So again, all we have to do is we start with the DFT formula, x of k summation n from 0 to n minus 1 xn e to the minus j 2 pi k over n times little n. My xn is a n, so I get summation n from 0 to n minus 1 an e to the minus j 2 pi k over n times n. Again, you always want to turn it into a geometric series, so I write it as n from 0 to n minus 1 a times e to the minus j 2 pi k over n whole power n. So this is sort of my r. So I just now use the geometric series formula. I get 1 minus, it's called r to the total number of terms. So my r is a e to the minus j 2 pi k over n, and the total number of terms I have are capital N, right, over 1 minus a e to the minus j 2 pi k over n. Now I'll just take the power. I get 1 minus a to the capital N e to the minus j 2 pi k, because capital N cancel with capital N, and I get 1 minus a e to the minus j 2 pi k over capital N. Now this again, it's e to the minus j an even multiple of pi, so that is equal to 1. So I get 1 minus a to the n over 1 minus a e to the minus j 2 pi k over n for k from 0, 1 up to n minus 1. So this is a case where you are never doing the 0 by 0 division, and here I don't have to be careful about any special indices k. Okay. So that's about it for this part. So this is the second problem where you are given a sequence which is a complex sinusoid, but we are restricting the complex sinusoid to just n minus 1 samples. Okay, because we cannot, in this class we are not talking about computing the DFT for infinite length sequences, so we are restricting it to n samples. And the first part is that we are asked to compute the DTFT now. Okay, the purpose of this problem is to be able to understand the relationship between the DTFT and the DFT. So part A is simply saying compute the DTFT. So the DTFT is x e to the j omega is summation n from minus infinity to infinity xn e to the minus j omega n. Now we are considering xn only from 0 to n minus 1, so we get n from 0 to n minus 1. My xn is e to the j omega naught n e to the minus j omega n. So I just simplify that, e to the j omega naught minus omega n. Okay. Now after this, it should be rather simple. So this is like my r, and I have r to the n. So I have a geometric series. So I get 1 minus r times r to the total number of terms. So I have e to the j omega naught minus omega capital N over 1 minus e to the j omega naught minus omega. Okay. This is my DFT, a DTFT of the finite length sequence. So part B of this problem asks you to remember the relationship between the DFT and the DTFT. Part B is saying without explicitly computing the DFT. So you could use the same sequence and you could compute the DFT explicitly using the DFT formula, but part B is saying you cannot use the formula, but you still have to specify the DFT. How do you do that? Well, for that, we have to remember the relationship between the DFT of a sequence and the DTFT of the sequence. The relationship is that DFT xk is equal to the DTFT sampled at omega equal to 2 pi k over capital N. Okay. DFT is nothing more than samples of the DTFT of your sequence. So all I have to do is this is my DTFT. I just sample it every 2 pi k over n. So this means that x of k equals to 1 minus e to the j omega naught minus 2 pi k over capital N times little n over 1 minus e to the j omega naught minus 2 pi k over n. This should be capital N. I could have gotten the DFT using the DFT formula explicitly, but the purpose of this problem is to remind you the relationship between the DTFT and DFT. If you are given the DTFT, you can simply compute the DFT by taking samples of it. Okay, the last part, and that is something that you should always try to remember. The last part is saying, now I have my frequency omega naught, which is a multiple of 2 pi over capital N. So previously, we didn't assume anything about omega naught. Now we are saying it's a multiple of 2 pi k over 2 pi over n. It's a multiple of 2 pi over n. So we are given omega naught equal to 2 pi k naught over n, where k naught is an integer. What is the DFT in that case? Well, I simply replace that. I get x of k equal to 1 minus e to the j 2 pi k naught over n minus 2 pi k over n times n over 1 minus e to the j omega naught minus 2 pi k over n. Okay. What the question is asking is, previously we were told that we have xn, which is just some sinusoid with frequency omega naught. That is any frequency, and we are looking at it from 0 to n minus 1. Now the question is, what happens if that frequency was a multiple of 2 pi over n? Okay. What does the DFT look like in that case? And that's what we are trying to address. So if you have a frequency which is multiple of 2 pi over n, this is what we get. Let's simplify this a little bit better to see what the output will be. So I get 1 minus e to the j. I am going to take 2 pi over n common. I get k naught minus k times 2 pi over n times n over 1 minus e to the j omega naught minus 2 pi k over n. Okay. I should actually replace this omega naught 2 with 2 pi k naught over n, and then simplify this further. E to the j k naught minus k over 2 pi over n. So let's take the case where k is not equal to k naught. If k is not equal to k naught, what does x of k look like? In that case, x of k is 1 minus, so I have this capital N cancels with capital N, 1 minus e to the j k naught minus k times 2 pi over 1 minus e to the j k naught minus k 2 pi over n. So when k is not equal to k naught, first of all, my denominator, this is not equal to 0. Okay. And what about the numerator? Well, k naught minus k, if k naught is an integer, k naught minus k is an integer. And so this is just an even multiple of it. This is like e to the j, some even number, times pi, right? Because k naught minus k is an integer, it is getting multiplied by 2, so you get an even integer, and you are multiplying that by pi. What do you get by Euler's identity? So this thing is 1, and we get 1 minus 1, we get 0. So if your frequency was a multiple of 2 pi over n, your DFT is 0 for all indices that are not equal to k naught. Now what about the case of k equal to k naught? Now take k equal to k naught, okay? If you do that and you try to plug it in directly, what do you get? K naught equal to k, so this is 0. Then denominator is 0 and the numerator is 0. So you can't explicitly do that calculation. So for k equal to k naught, I'll just say that x of k naught equal to summation n from 0 to n minus 1 xn e to the minus j 2 pi k over n times little n. So I'm going to replace the value of xn, which is e to the j 2 pi k naught over n times little n e to the minus j 2 pi k over n times n. So this is x of k. And now we are interested in the case where k equals to k naught. So if I replace this k equal to k naught, then what do I get? This whole thing is equal to, it's e to the j theta times e to the minus j theta. That's just 1. So this, each of the terms is 1. I have n of these terms. I get capital N. Okay. So my DFT is given by 0, k naught equal to k naught, and n k equal to k naught. Okay. Effectively, what you are seeing is that if you were to plot your DFT, you will get k equal to 0, 1, 2, 3, and then at k equal to k naught, you get a spike, and then you get zeros again, up to n minus 1. This is for the case where xn equals e to the minus j 2 pi, e to the 2 pi over n times k naught n. Okay, where your frequency is a multiple of 2 pi over n, and you take an endpoint DFT, what you get is just a spike at k naught, the factor by which you are getting the multiple of 2 pi over n, and everything else is 0. So having done a few of the DFT exercises, which gives us the main tools that we use for computing the DFT and the relationship between the DTFT and the DFT, let's now move on to other properties that we have studied while doing the DFT. So this is an example which says you are given two 8-point sequences. This is x1n, this is x2n, and you are asked to write x2n as a function of x1n. Okay. They are two completely different sequences, but they are both length 8 sequences. They go from 0 to 7, and you are asked to express them in relation to each other. So if you look at it, this is what is happened is that this ABC has been moved here, and this DE and the next two zeros have sort of come back. So this part has come here. So this is this part, and this part is here. So this is just the circular shift operation that we had studied. Okay, and this is a circular shift by my 0 has moved to 4, and this is just a circular shift by an amount 4. So x2n is nothing but x1 of n minus 4 mod 8. Okay, so this is a mod 8 circular shift, and we have shifted our sequence by 4. This practice problem is about a review of circular convolution. So we are given two sequences, and we are asked to compute circular convolution, which is a 6-point circular convolution. So let's call yn as the output of this circular convolution, x1n, circular convolution 6-point x2n, and remind ourselves what the circular convolution looks like. Okay, circular convolution is simply just like linear convolution. You fix one sequence, you circularly flip the other, and then you circularly shift the other sequence. So I have m from 0 to n minus 1. Now in this problem, I want to basically fix x2n. Okay, so I'll have x2 of m is fixed, and then I have x1 of n minus m, which is just like linear convolution, but I have actually, instead of linear shift, I have circular shift. So this will be xn minus m, and this will be mod. So it will be x1 n minus m mod 6. Okay, and that's about it. Now we have looked at circular convolution in doing graphically or in a tabular fashion, but for this problem actually it's much simpler than that. Okay, for this problem I'll just plug in the values. x2 of n is 0 for everything except n at n equal to 2. So x2 of n looks like this. I am treating x2 of n as a length 6 sequence. So I have at n equal to 0 it is 0, n equal to 1 it is 0, at n equal to 2 it is 1, and then it is 0 at 3, 4, and 5. So 3, 4, and 5. So I can actually just directly write it down. I get all the terms, since they are getting multiplied by x2m, every term in this summation is going to be 0 except for little m equals to 2. So I'll get x2 of 2 times x1 of n minus 2 mod 6. Now what is x2 of 2? That is just 1. So I get x1 of n minus 2 mod 6. So what is the output of your circular convolution? It is just circularly shifting your x1n by 2. Okay. So your x1n was, this is n equal to 0, 1, 2, 3, 4, and 5. Your x1n is n plus 1. So at n equal to 0, it is 1, 2, 3, 4, 5, and 6. This is your x2 of n, and this is your x1 of n. Okay, and your circular convolution answer is x1 n minus 2 mod 6. So what would that look like? I am going to shift everything by 2, and when I reach the end of 5, whatever are the remaining two things, I wrap them back. So this x1 will actually look like the following. I'll have 0, 1, 2, 3, 4, 5. So my 0 gets shifted to 2. So I have this, and you keep on going, and at 0 I will get actually whatever was at 4. So at 4 I had 5, and at 1 I get 6. Okay. And at 2 I get 1. So this is my circular shifted copy. Now, the reason we did this exercise is just to actually relate it to the case of linear convolution. This is a very special property that you should try to keep in mind. Your one of the signals is an impulse, a shifted impulse, right? X2n is an impulse at n equal to 2, and x1 is just sequence. If you were to linearly convolve x1n and x2n, what would you have gotten? If you linearly convolve a signal with a shifted impulse, what is the effect? Linear convolution with an impulse simply gives you an output which just shifts the sequence to the location of the impulse. Now let's ask the same question in the case of circular convolution, which is this example. We are circularly convolving a signal with an impulse. What we get is a signal, instead of linearly shifted to the location of the impulse, we get a signal which is circularly shifted to the location of the impulse. Okay, so you almost get back the same relationship, but instead of a linear shift to the location of the impulse, you are getting a circular shift to the location of the impulse. This is a practice problem which is again for circular convolution. Now this practice problem is a little more involved, so we perhaps want to, instead of using just the direct formula for circular convolution, it is better if we actually use our tabular method for the circular convolution. Okay, so we can write down the formula for circular convolution, which is n from 0 to 5, because we are doing a 6-point circular convolution. And this will be h of m, x of n minus m, just like linear convolution, but now we have a circular shift, so a mod of 6. Okay. But if you were to do that using this explicit formula, it can be a little tricky to do. So instead, we will use the tabular version of circular convolution that we had seen. So we'll just create for different n's. So we are interested in output, we get n equal to 0. So if we are doing 6-point circular convolution, what is the length of our output sequence? So length of our output sequence is 6, so we go from n equal to 0, n equal to 1, n equal to 2, n equal to 3, 4, and 5. Okay. So we just start with that. And each of these columns will give us an output. Now for n equal to 0, we fix one sequence. So let's fix h of 0. Right? So h of 0, let's fix h of m. So h of 0 is 1. H of 1 is 1. So let's write this down. My h looks like I have 1 at 0, 1 at 1, 1 at 2, and then I have 3 zeros. So I get 1, 1, 1, 0, 0, 0. Okay. Since I'm fixing this, I should just repeat that in each column without any looking at anything else. 1 1 1 0 0 0 1 1 1 0 0 0. Okay, so this takes care of my h. Now I have to start off with a circularly flipped version of my x. So what does my x look like? My x is given by, so at n equal to 0, my x is 6. At n equal to 1, my x is 5. Then it is 4, 3, 2, and 1. Okay. 2, 3, 4, 5. Now, the first column is always the circularly flipped version of the sequence that you are not fixing. So what's the circular flip? What I'm interested in is I need to calculate x of minus m mod n, which is x of minus m mod 6. Okay. Now, we had done the circular flip version. What was that? This is equal to, so for m equal to 0, we get back 0. Minus 0 mod 6 is 0. But for every other thing, we get x of n minus m. Right? So this is equal to x of 0 for m equal to 0, and x of n minus m, which is x of 6 minus m for m not equal to 0. So what do I get for here? X of 0. Right? So I get x of 0 is 6. I'm multiplying 6. I'm just writing down this formula for each n. And what do I get next? What is x of minus 1 mod m? That is, so this is x of minus 0 mod 6. Right? The next term will be x of, this needs to be x of minus 1 mod 6. That will be actually x of 6 minus 1, which is x of 5. So x of 5 is 1. So I get 1 here. And then I just start reading from the backward thing. So we circular flip, we fix this, and we are just going to start reading from this side. This, then this, and this. So I get 1, then I get 2, I get 3, I get 4, and I get 5. And then what is my then y of 0? Y of 0 is simply we multiply these and we add them all up. So I get 6, 1, 2, 0, 0, 0. I add them all up, I get 9. Now, what do we do for y of 1? You can try to go back to the circular flip, but we have talked about all that you have to do in the next column is basically just shift all of this column of x downward, and then whatever is going below, you just put it back up. So what you get here is 6, 1, 2, 3, 4. 5 has no place to go down, so that comes up back up. Okay. And now we just multiply these and add these. So what do I get? 5, 6, 1, and the rest is 0. So I get 5 plus 6 is 11 plus 1, 12. The next column, I do the same thing now with this version. Okay. I'm going to shift all of this column down, and then whatever is left, I just take it back up. So I get now 5, 6, 1, 2, 3, 4 is left, that comes back up. So I multiply that, I get 4, 5, 6, and the rest is 0. So y of 2 is 6 plus 4 is 10 plus 5, 15. The next one, I again just shift this whole column down. I get 4, 5, 6, 1, 2, and 3 goes up. I get equal to 3, equal to 4, 5, the rest is 0. I get y of 3 equal to 5 plus 7, 12. I shift it again down. I get 4, 3. So I get 3, 4, 5, 6, 1, and 2 goes up. I get 2, multiply that, 3, multiply that, get 4. The rest is 0. I get y of 4 equal to 2 plus 3, 5 plus 4, 9. Okay. The last one is, again, shift everything down, 2, 3, 4, 5, 6, and I get 1 here. So 1, 2, 3, everything is 0. I get y of 5 equal to 6. Okay. So my output looks like I have first 9, then 12, 15, 12 again, I have 9, and I have 6. So this is my output, n equal to 0, 1, 2, 3, 4, 5. This is my yn. So this helps us basically remember concepts of circular shift, concepts of circular convolution, how to compute the DFT of a sequence, what is the relationship between the DFT and the DTFT, and there are some other properties that we haven't formally done their problems, but if you just remember these key tricks, you can move forward from here. So let's now move on and talk about the case of what is the relationship of DFT to DTFT and how is that used to do spectral analysis of a signal. So this problem is related to that. We are given a continuous time signal which is band limited to 5 kilohertz, and then we sample it at 10 kilohertz. Okay. And once we sample it, we compute the DFT, 1,000-point DFT of our XN. So we had done this lecture on how can DFT be used to tell us what is happening in continuous frequencies. And this problem is effectively asking you to relate the DFT sequence values to the continuous frequencies. Okay. So part A is saying once you compute the DFT for k equal to 150, which frequency does that correspond to in continuous time? So the way you want to solve this problem is you want to remember that DFT is related to DTFT. Okay, you need to remember that relationship. What is the relationship? DFT is samples of the DTFT from 0 to 2 pi minus 2 pi over n. Okay, it samples every 2 pi over n radians. But now we want to relate it back to the continuous time. So for that, you have to remember the relationship between the continuous time frequencies and the discrete time frequencies. What is that relationship? It's a rescaling of the frequency axis. So the sampling relationship that we had done earlier. So you want to go through that in 2 steps. Okay. So what is the first step? That x of k is related to x of e to the j omega by sampling it at 2 pi k over n. Okay. Now, when we are connecting DFT to continuous time frequencies, it's important for us also to be aware that we must relate the DFT to the little omegas which are between minus pi and pi. So technically DFT samples DTFT from 0 to 2 pi. Right? Remember, x of 0 corresponds to little omega equal to 0, and x of n minus 1 will correspond to little omega equal to 2 pi over n minus 1 over n, which is simply 2 pi minus 2 pi over n. So DFT samples DTFT by going beyond pi. And so what you have to be careful is, we had done those expressions a few lectures back, that if your index is bigger than such that you go above pi, you have to bring it back by subtracting 2 pi so that you remain within the minus pi to pi range. Okay? So we have to be careful when we are doing this relationship, because at the end of the day we want to relate our index to continuous time frequencies. So what is our little omega in this? For k equal to 150, this means, let's call it little omega k, that is equal to 2 pi k over n. For k equal to 150, that is equal to 2 pi times 150 over my capital N is 1000. Okay, so that is 300 by 1000 pi, that is 3 by 10 pi. Okay, is 3 by 10 pi outside the minus pi to pi range? Since 3 by 10 pi is not outside our permissible range, we are fine. We say that k equal to 150 corresponds to little omega equal to 3 pi by 10 pi radians, discrete time frequency. Okay. Now the question is not asking about what does that correspond to in discrete time frequency. The question is asking what does that correspond to in continuous time frequency. So we have right now just addressed this part of the problem. We have addressed this. We now need to remember this part of the problem, and then we will combine the two. So if I am given little omega radians, what is that in continuous time? Which frequency is that in continuous time? So omega radians in discrete time, that is equal to omega by t radians per second in continuous time. What is our capital T? It is 1 by 10,000. Right? It's 1 over 10 kilohertz. So our Fs is 10 kilohertz, which means that T is 1 over 10,000. So 1 over 10 to the 4. So we know this relationship. So we just now connect the two pieces. So k equal to 150 corresponds to, we calculated little omega to be 3 by 10 pi, and now we divide it by capital T, which is, we divide it by capital T, so we get 3 by 10 into 10 to the 4 pi, okay, or which is 3 times 10 to the 3 pi radians per second. Okay, or you could say that that is equal to 1.5 kilohertz. Right. So if you look at what this means is, if you look at the 150th sample of your DFT, that is telling you something about what is happening at 1.5 kilohertz frequency in continuous time. So let's now go to part B of this question, which is a little tricky, but hopefully if we remember the discussion that we had in part A, we shouldn't be in any trouble. Now we are dealing with index k equal to 800. So we do the same process. We have part B. Again, we want to do DFT to DTFT and DTFT to continuous time Fourier transform. Okay. So k equal to 800, this means we are dealing with little omega equal to 2 pi by 1000 times 800 radians. That is equal to 1600 by 1000 pi radians, or 16 by 10 or 8 by 5 pi radians. Okay. So this is correct. There is no issue there. We have solved this part. But remember, the relationship between the DTFT and the CTFT requires us to work with a frequency which is between minus pi and pi. Now 8 pi over 5 is bigger than pi, right? 8 by 5 is bigger than 1. So we cannot use this relationship alone to go to the continuous time frequencies. What do we need to do? We need to bring it back to the principal period of discrete frequencies. So discrete frequencies are 2 pi periodic. If we want to get that, what do we have to do here? So an immediate way of seeing this should have been actually that k is bigger than n by 2, and whenever you are bigger than n by 2, actually you have to do this sort of bringing it back into the minus pi to pi range. So this omega is 8 pi by 5, but that is also equal to, because of the periodicity of discrete frequencies, that is equal to 8 pi by 5 minus 2 pi. Okay, which is 5, 8 minus 10 minus 2 pi by 5 radians. Okay. So now we are in the minus pi to pi range. And now we can talk about the relationship between this frequency and the discrete and the continuous time frequency. So we have k equal to 800 is equal to minus 2 pi by 5 radians little omega. Now what is the relationship of that to discrete to continuous frequencies? What do? We divide it by t. So we get 2 pi over 5 times t radians per second, which is equal to minus 2 pi over 5 times 10 to the 4 radians, okay, which is minus 20 by 5 10 to the 3 pi, or minus 4 10 to the 3 pi. So in hertz, that will be minus 2 kilohertz. So if you look at your k equal to 800 index of the DFT, that is telling you something about minus 2 kilohertz frequency. Okay, this is the last practice problem that we are going to cover today. It is also about the spectral analysis, but instead of the previous case, it is now asking us to decide what values of t and n should we use if we want to do certain type of spectral analysis. So let's look at the details of this problem. Of course, we have to make the usual assumption that I'm dealing with a continuous time signal and it is band limited to 5 kilohertz. And then you sample it with a time period t to get xn. Now the sequence may be infinite length, but we are going to work on the first n samples, and we are going to compute the endpoint DFT. So what is the challenge that is given to us? That we need to find the smallest n that we need to use and the range of frequencies that we need to use so that aliasing is avoided. So if it was just that aliasing is avoided, the answer is simple. But we also want to make sure that the DFT samples are giving us information about continuous time frequencies which are no more than 5 hertz apart. Okay? So again, we have to remember the relationship between DFT and DTFT, and then DTFT and CTFT. Okay? So first of all, let's talk about what is the constraint that we get if we want to make sure the samples are giving us information less than 5 hertz apart. So what is 5 hertz? 5 hertz means 10 pi radians per second. Right? So this is one relationship that we know. So now we know that DFT samples the DTFT every 2 pi over n radians. Right? So the gap between two DFT samples in discrete frequencies is what? Gap between two discrete frequencies is 2 pi over n radians. Now we are interested in making sure that the DFT gives us no bigger gap than 5 hertz in continuous time. So this is the relationship between DFT and DTFT. We also know the relationship between DTFT and CTFT. So 2 pi over n radians gap in discrete time, that is equal to how much gap in continuous time? What do we do? So 2 pi over n radians gap in discrete time is 2 pi over n divided by t, which is 2 pi over nt radians per second gap in continuous time frequencies. Okay? So what we are told is that this gap should be no bigger than 10 pi radians per second. So our first constraint is that 2 pi over nt should be less than or equal to 10 pi, which means that 2 or 1 over nt should be less than or equal to 5. Right? That is my first constraint. We are interested in finding both n and capital T. I have just one constraint. I have two unknown variables, so I need to find one other constraint. Where is that constraint going to come from? So our other constraint is that we must sample such that no aliasing happens. So what does that mean? That the other constraint is that my sampling frequency 2 pi over t should be bigger than twice the maximum bandwidth. So what is the bandwidth of the signal? It's 5 kilohertz or 10 pi. It's 10 pi 10 to the 3. Okay. So using these two constraints, I should be able to solve for both t and n. Okay. So I know that 1 over t has to be bigger than or equal to 5,000. This is my second constraint. And this is my first constraint. Right? So how now the question that I'm asked is that I should use n as small as possible. So if we want n smallest, then this means that to satisfy 1 over nt less than or equal to 5 constraint, we must have t largest, but t can't be larger than 1 over 5,000. So I just pick t to be 1 over 5,000. Okay. So if I pick t to be 1 over 5,000, I get 1 over t, 1 over n, 5,000 is less than or equal to 5. This means that n has to be bigger than or equal to 5,000 over 5 equal to 1,000. So I pick my n to be simply 1,000 because I am given n smaller. So I pick n equal to 1,000. That is one answer. And I pick t to be equal to 1 over 5,000 or 1 over t to be equal to 5,000. So I think I made an error here because my sampling frequency should be twice the maximum bandwidth. The maximum bandwidth is 10 pi 10 to the 3. So I forgot to multiply by a factor of 2. Okay? So I should have a 2 everywhere. And that is, so this is 5,000. Instead of 5,000, I should have 10,000 everywhere. And I get 10,000. And that will be 2,000 then. So my n is actually 2,000 and t is 1 over 10,000 or 1 over t is 10,000. So I made an error at the Nyquist criterion, the aliasing, and that's why my sampling frequency was coming out to be the same as the maximum bandwidth, which is of course an error because my sampling frequency needs to be at least twice the maximum bandwidth.